All right, let's dive right into this explainer. We're going to take some wonderfully dense physics math and transform it into visual building blocks that you can actually see and intuitively understand. If you've ever wondered how physicists mathematically describe the precise motion of a rocket, the push of gravity, or the torque on a spinning wheel, well, you are in the exact right place. We are going to decode the structural language of the universe's motion. First up, we've got to separate two completely different types of physical quantities. On one side, you have simple quantities that just have a magnitude. Think of things like mass, or the absolute temperature of a room. A simple number does the trick perfectly. We call these scalars. But on the flip side, we have things where direction absolutely fundamentally matters. Think about a physical push or the velocity of a plane. You can't just tell air traffic control you're flying 500 miles per hour. They really need to know if you're heading north to Canada or south into a mountain. In those cases, direction is survival. And those are vectors. So here is our roadmap for mastering this foundational concept today. We'll meet the vector, add things up, scale and reverse them, break vectors down, and finally look at the math of vectors. Section 1. Meet the vector, the arrow of physics. So what exactly is a vector? Well, it's a physical quantity that holds two crucial pieces of information at the exact same time, direction and magnitude. Unlike a scalar, a vector can stretch, shrink, and completely reverse its trajectory based on the physical forces at play. Position, displacement, acceleration, force, momentum, these are all vectors. And physicists really needed a clean, intuitive way to represent this dual nature math. Look at how we can turn an abstract math concept into a really simple, highly visual geometric arrow. We denote a vector, like vector A here, with a little arrow over its letter. The physical length of this drawn arrow directly corresponds to the magnitude, the absolute power or strength of the force. And the arrowhead itself? That points in the exact direction the physical quantity is acting. It's honestly just elegantly simple. Section 2. Adding things up, combining forces. Now, imagine you've got two forces pulling on a single object at the same time. To find our total resulting force, we use a super visual geometric construction known as the tip-to-tail method. It's pretty straightforward. You simply draw your first arrow, A, then you place the tail of your second arrow, B, right at the tip of A. Finally, you just draw a brand new vector from your starting point all the way to your ending point. And there it is, vector C, right in the middle. It's the new combined vector you get by tracing a path from the very start of A's tail straight across to the final tip of B. This single arrow, vector C, represents the exact equivalent of forces A and B acting together on that object. But here is a really crucial point, which is the commutative property of vector addition. It literally doesn't matter whether you start by drawing vector A first or vector B first. If you draw them both from the exact same starting point, they actually form the sides of a parallelogram. And the diagonal of that parallelogram, that's your vector C. You land at the exact same physical destination regardless of your starting order. So, A plus B is exactly the same as B plus A. And it's the exact same logic when you have three or more vectors acting at once. The associative law basically proves that no matter how you group them, whether you add A and B first and then add C, or add B and C first and then add A, the final vector sum remains absolutely identical. The physical universe really doesn't care how you group the math. Whether it's wind, gravity, and engine thrust acting on a plane, the resulting flight path is going to be exactly the same. Moving on to section 3, scaling and reversing, multiplying by numbers. In physics, we constantly need to scale a force up or down. So if you multiply a vector by a real number, which remember we call a scalar, you are simply stretching or shrinking the length of that arrow. If you multiply vector A by 2, you literally just draw the arrow twice as long, keeping it pointed in the exact same direction. But what if you multiplied by a negative number, say -1? Well, the magnitude stays exactly the same, but the direction completely flips, exactly 180 degrees. This gives us what is called the vector's inverse element. It's pretty cool because if you add vector A to negative vector A, they cancel each other out completely, bringing you right back to 0. Section 4. Breaking vectors down, the coordinate plane. Now, floating arrows are great for concepts, but to solve actual physics problems, we have to anchor them to an XYZ grid. To do this, we define something called unit vectors. You'll usually hear them called I hat, J hat, and K hat. These basically act as the pure directional DNA for our grid. They have a magnitude of exactly 1. The I hat strictly points in the positive x direction, j hat points in the positive y direction, and k hat takes the z direction. They are what allow us to translate geometry directly into algebra. Check out how this diagonal vector doesn't just float randomly in space anymore. It is decomposed into a combination of a horizontal x component stretching along the x-axis and a vertical y component stretching up the y-axis. It's almost like finding the vector's shadows on the walls of our grid. By isolating these individual components, we can actually deal with complex diagonal forces as simple straight-line numbers. Finally, Section 5. The math of vectors. Calculating reality. So what if we only know the x and y components, but we really want to find the total magnitude of the force? This is basically the core problem physicists face every single day, bridging the gap between independent measured parts and the combined reality of the total force. If our sensors only give us the horizontal push and the vertical push, how on earth do we find the power of the diagonal result? Well, because our decomposed components form a perfect 90-degree right triangle on the grid, the math actually becomes incredibly friendly. We can simply use the good old Pythagorean theorem, a squared plus b squared equals c squared, to find the total length or magnitude of our vector. And to find the specific direction, we just use basic trigonometry, like sine, cosine, and tangent, to pinpoint the exact angle. By knowing just the x and y components, we can easily calculate this angle, which we call theta. Taking the inverse tangent of the y component divided by the x component gives us theta, placing the vector perfectly and mathematically within our coordinate universe. Just like that, you've transformed a physical arrow into a precise, calculated trajectory. And here's the best part. When you need to add complex vectors together in a real-world scenario, you definitely don't need a ruler and protractor to draw them tip to tail. You just mathematically add all their x components together to get a total x and all their y components together to get a total y. Then you reconstruct your final total vector, c, using the exact same Pythagorean theorem and trigonometry we just talked about. It's elegant, it's highly scalable, and it is completely precise. So you now possess the structural language of the universe's motion. This algebraic and geometric toolkit is literally what's used to map out the physical world. Every video game you play, every bridge you drive over, and every satellite up in orbit relies on this exact math. The universe is practically written in vectors. So whose reality will you calculate next? Keep exploring, and I'll catch you in the next explainer.